Welcome back, fellow computer touchers, part-time gardeners, and also aspiring programmers. This is day 63 of Daily LeetCode. Daily LeetCode. We are back once again. We are continually being tormented by. Evaluate division. Right. Yesterday we did some other problems like balanced binary tree, right? And then we went to evaluate division. Overall, I have to reflect on the way the current system is going. I'm noticing a pattern when I watch these videos back. I say I'm going to do one thing and then I do something completely opposite. And I think that's partially because that is something that helps me continue working through the problems. So I guess, for example, trying to build a long-term habit of learning and curiosity, right? I find that for myself, locking myself into a very, very rigid structure to some degree can sometimes turn me off completely. So it's something I try to be careful of. But I noticed that, right, I can sit down to do the problems every day and read and watch the system design architecture lectures, but I also have to leave some space for me to explore as well, right? So I can kind of keep my interest there. That being said, Thomas, the GOAT himself, Thomas mentions that we need to do the weekly contest, brother. Now that is true. That is true, right? And that would be a good thing to do. I was just taking a look at it. The contest, right? But at the same time, I wanted to take a more structured approach to learning. So it's tough. I want to do the contest, but at the same time, I want to make sure that I'm making progress through the things that we need to be making progress through. That being said, I'm thinking that the only thing I want to continue my original plan of getting these a set number of problems. I think we have about 30 problems remaining, right, that we've done in the past that I'd like to completely ingest into our brain membrane, right? 30 or so problems, right? And it's crazy because I learned so much from redoing these problems. It's crazy. Especially while reading the ADM. For example, there's another problem, climbing stairs, that I want to try some new tactics on. I want to try snakes and ladders again. I also want to try coin change again, right? A lot of these shortest path are problems that can be rephrased as shortest path problems, right? I kind of want to try these new things. That being said, I think we might have to do something completely drastic, right? We may have to stick to, I don't even know if I can say it, only review. And I think this might be the wave. This is precisely because there's just, from the previous, right, sprint of problems, it was like 2 weeks ago, I was doing like 6 hours a day, right? There's just a crazy amount of backlogged problems that need to be completed, and it's just creating a big inefficiency in the process. So I think we need to ingest all of those gems from those old problems, right? And then we can continue with the new problems. And I think we're going to come back better than ever after ingesting all those problems. The problem is, if you look at it from a short-term or if you look at it from a short-term point of view, I don't think it's going to give the greatest. I think it's going to give some pretty great gains, right? But we're also not going to get it as exposure to many problems. But I think that's the cool thing with depth. Like when you really, really get something, you can do a lot more with a lot less. So that's kind of what I'm going for. And I think it might just have to be something we accept going forward. I'm going to have to continue doing review, right? And that could take a month, I think, to get through all the review problems. But at a steady pace, I think we should be fine. But yeah, I think it's just a necessary evil at this point. It is unavoidable. I hate to say it. It's going to be monotonous. It's going to be mundane. But I think there's some value there, because I think what's really cool is that we haven't really solved very many problems. But from the problems we have solved, we've been able to make the information we've learned from them portable, right? To take them into new problems. So I think that's the goal. But yeah, I think, it's just a necessary evil. That being the case, we have no cards due today, which is good because that means we can pound through a lot of problems. And I think the other beautiful thing with review, as I'm reading through the algorithm design manual, right, the holy text of algorithm design by Siena et al. And the other holy authors of this text, as I'm revisiting these old problems, I'm seeing new ways to try and tackle these problems, or new ways to raise the time complexity that I'm used to solving them for. So I think there's just so much to be gained, right? And it's a weird thing where you're solving a problem, right, and you may not get to the solution, but just being able to rule out a subset of potential solutions, right, by trying them or thinking them through, I don't know, there's just something magical about that power. And I guess later on, right, later on it's going to be easier to go about doing some of these things, because I think it's going to be, I'm talking really general, it's going to be easier to solve problems, because hopefully by really taking a closer look at the requirements of a problem, or I guess the key indicators of that might be leading you to a particular solution, right, or framing of a problem, right, we should get much better at identifying which ones automatically will not work, right? And that's what is unknown when we review problems, right? Sometimes I did a problem in the past, right, and my solution works, but I'm making a lot of assumptions that I'm not even cognizant of. And I think that's a bad habit, because I don't really know exactly why. Like, what are the key fundamental principles that allow this to work, right? So the ADM is doing that, right? At the same time, we need to build our ability, we need to build our intuition. That being said, spiel over. That is all I wanted to say. I think we're just gonna have to do a review. It remains to be seen. I think today we can keep ourselves on track and only do review. I think tomorrow, right, if I start doing the wrong thing, if I'm not doing review, type me a message and say, like, yo, bro, you need to stop it. Like, you need to tell me, like, hey, get some help, right, and then I'll stop. But also, some other cool things as well. The channel has been growing pretty cool, pretty well. So that's pretty cool. It's cool to see that, you know, the community is slowly growing, and like, met already some cool people like Thomas, I'm Just That Guy, the Copy Ninja. We also had some people join Discord yesterday. So it's just really cool to see, right? Because the lifelong habit of learning and curiosity is pretty magical in and of itself. Feels strong, man. So that's pretty cool, right? Other things as well, reflections on other things. So it seems right now, daily, right, my time limit, right, for these problems is about an hour. And I think that's just a necessary evil as well. I used to go for an hour and a half, but I'm trying to also attack my weakest areas. That also being system design. I know nothing about a system, you know, or a design. So I'm learning a lot, right, from David Mallon's lectures through Harvard, right? And I'm following the system design primer by Don Martin. So this is really cool, right? So I try to do 30 minutes of that. 30 minutes of the system design, 30 minutes of reading the algorithm design manual, and then an hour of LeetCode problems, right? And that, I think in the last week or so, or last 2 weeks or so, we've really made a lot of progress, which has been cool. But I think that's the new wave, but it comes with an added evil that the daily videos are going to be slightly shorter, right? I think I could record myself watching the lectures and reading through the book, but that seems a bit strange. So I don't know. Maybe it's not strange. Maybe it's interesting. So if it is, maybe someone can leave a comment and say, "Hey, don't do this, brother," or "Hey, do this, brother." So yeah, I don't know, but I think that is the goal for now. Other reflections, right? Yeah, I think that's the wave, and I think I guess just reflecting on other things as well. I think I felt a very big pressure to learn as fast as I could, right? But I think that might have been because I was time boxing myself, right? Ideally, you know, you want to optimize for the long term, so that optimizing for the long term sometimes can really help optimize for the short term. So sometimes rushing through problems or trying to solve as many problems or getting like the LeetCode number counter up, right, just makes things take longer, right? So yeah, I think I felt that pressure. I think now I'm slowing down. Right, not to say that the videos are going to slow down at all. The videos will keep coming until the end of eternity, hopefully, right? But I guess in another sense, what I'm getting at is that I was kind of rushing, right? Kind of doing, maybe some days I would do 6 hours minimum. At the time, I was doing an hour and a half, right? So I was always the LeetCode part that is recorded, right? And then the other half would be like off recording. I'd be reading and other stuff. So I think the days of doing 6 hours of review and other stuff, I think there's always a time and a place for it. I think long term is unsustainable, and yeah, I mean, learning is important, right? But ideally, the reason we learn is so we can apply. So also got to balance that with doing things away from the computer, right? And growing the knowledge base in areas other than computer science, like in multiverses. So you're going to want to make sure after you do an hour of LeetCode that you do an hour of multiverses, right? So that being the case, you're going to want to join the HCC. This is the Hyperbolic Coding Chamber. Thousands of people are joining every single day and finding the new tips. And you're going to find a lot of channels called 6 tips to getting your next position, or 6 keys to solving all LeetCode problems, or secret cheat codes for different platforms, right? So you're going to want to join. And yeah, I mean, we're going to have a surprise musician appearance, right? This person has about 8 billion streams on Spotify. They're going to be joining the Discord on Friday, so you're going to want to join, right, because of that. So yeah, I mean, that's the HCC. We have tons of large brains in there, right? And it's kind of just me also in there trying to blend in with the other large brains, but I'm secretly a small brain. So that is the case, right? If you made it this far, thank you for watching, right? And if final thing, I want to start making those coding tutorials as well. There's a lot of problems we have a good grasp on that I also want to release a video for. So yeah, I don't know how we're gonna squeeze it all in. So it is going to be tough. It's also possible that I've done a lot of these problems already, so I could just cut up the problems I'm already doing as individual videos. So that's also interesting as well. So that being the case, right? We have 1 hour on the clock to dunk on some LeetCode problems, right, that we've seen before, but hopefully some of them, right, we're going to try and take them in a new direction, right, that we haven't taken them before, hopefully gather some new information, hunter-gatherer style. So let's just jump into it, right? Make sure to join the HCC. This is day 63. Let's do it. Time, our goal is linear time, linear space. All right, so let's just paste our goal in here so we don't forget it. So given the root, let me make sure everything's centered and makes sense. Given the root of a binary tree, return the vertical order traversal of its nodes' values. Vertical order traversal from top to bottom, column by column. If 2 nodes are in the same row and column, the order should be from left to right. So that's a lot. Let's map this to our example. Given the root of a binary tree, so we're given 3, turn the vertical order traversal of its nodes' values. It looks like that output is 9, right? 3 and 15, which is the output here, 20, right, and 7. So if we look at this verticality, right, they're also colored so that we can see, right, and they wanted to return it from top to bottom, column by column. 2 nodes are in the same row and column, same row, same column, the order should be from left to right. So right, this statement actually doesn't make sense for this graph. I think what they mean is this graph. So these 2 nodes, 0 and 1, would be in the same column, right? 0 and 1 and 3 would be in the same column, right? And the order they want is top to bottom, right? And then left to right. So 3, 0, 1. The output here is 3, 0, 1, right? So if we're wanting this, I think what we can see to start, right, is that ideally we're going to want to use a breadth first search, right? Because they're wanting a top-down ordering, and that's something that's going to be inherent to a breadth first search, because it's also called a level order traversal, which typically means going from top to bottom. All right, we have another problem is that we want them in groups of columns, right? And so what we can actually do is if we imagine this top node here, 3, right, as being in column 0, right, what we can do is whenever we go left, we can subtract 1 from that column. So 9 will actually be column -1. Then 4 will actually be column -2. right? And then the 9 sub 0, I mean 9, the right subtree here, right, going to 0. If 9's column is -1, then 0's column must be 0, right? Because when we go to a right subtree, we're going to add 1, right? And then when we go to 5, we're going to go left once, right? And so what that means is, right, if this is column 0, this is going to be column -1. So these end up in the same column, right? So if that's the case, right, we have a mechanism for mapping, right, nodes to their specific columns. And once we have their columns, right, we can just, once we have their columns, right, we can actually just, once we have their columns, right, once we have their columns, we can group them, right? So we'll have, you know, maybe we'll have something like a map, right, where we have -2, right? That's going to be up to 4 in the map, right? In our column, let's see, our next column is -1. That's going to have 9 and 5, right? And then 0 is going to have 3, 0, and 1 in it, right? And column 1 is going to have values 8 and 2, right? And column 2 is going to have value 7. So if that makes sense, right, then we can basically give them the output they're looking for, right? If we were to sort this map by keys, right, then we can just take the values, right, and return them, right? Because we can see that that's our answer here. So we know that we can do a BFS or level order traversal, right, to create map of column IDX to, you know, a list of tree nodes, right? So if we do that, right, then we're going to also have to do one more thing, or we're going to have to sort by key. So if our BFS takes linear time and our sort by key takes at best n log n time, our sort is actually, our time complexity for this is actually going to be dominated by n log n sort time, or sort complexity, sorting time complexity. Right, this is going to be a problem, right, because it's possible that we can do this without sorting by key, right? So how could we do, if we could remove this sort, right, then what we could do is just, what we could do is just have linear time and linear space be our output, right? So let's look at what is the sorting accomplishing, right? What does sorting accomplish? And I think what we see, right, is that at the end, once we have this map, right, we want to sort it, right? So let's say our map actually looks like this, right? So it's all out of whack, right? We can't return this. So when we sort it, right, by the key, what we end up with is this perfect map, right, sorted by the column indices in the exact order we want. So what is it that we're trying to achieve? Well, we basically want a way to order, right, our arrays, right, by the columns themselves, right? And so we actually don't have to sort, right, because we can accomplish that using another method, right? For example, since our columns, right, since our column values are going to be sequential, right, -1, 0, 1, and 2, because you're either adding 1 or subtracting 1, right, all we really need access to is the lowest call, right, and largest call, right, because we can create this output array simply by iterating, right, lowest call is less than largest call, right, and couldn't we just do output dot push map, well, we're going to say lower call, right, or let's just say I is equal to lower call to start, right? We'll say, well, I is less than largest column, right? Don't we just want to say map dot get I, right? Because if that's the case, our lowest column is going to be -2, right? Our lowest column is going to be -2, and our largest column is going to be 2. So we're basically iterating over the range of -2 to 2, right? We're actually going to want equals here, right? And then we'll be able to create our output array that we're so interested in. So I think what we're seeing here is that to generate that sorted array, basically what we wanted to do, right, was have our output sorted by column. And we can do that just by iterating over the range of the smallest column and the largest column, right? So we're going to do a breadth first search with a level order traversal to create this map. And then instead of sorting, right, we're going to want to keep track of lowest call and largest call, right? And at the end we can iterate over largest call and smallest call, generate output. So let's try that, right? So how could we, the traditional implementation of the queue, right, is with of a level order traversal is with a queue. So I have a root node, right? But we want to be able to pretty much figure out what level we're currently in, right? We want to be able to know what level we currently are in based on the current node, right? So when we go left, we're going to subtract 1, right? When we go right, we're going to add 1. If that's the case, maybe we could do something like this, where we actually have an array of tuples, right? Because the root is going to start at column 0, right? And that way we can say that the queue, right, would be an array of tree node, right, and number, right? So basically an array of tuples, right? Then we're going to say, right, while the queue.length is not equal 0, right, means we still have nodes to process, right? Then here we're going to say, let's pull off the current queue off, let's pull off the current node off of the queue. To do that from the front, it's going to be cur.shift, right? So now we have this node, which is 3, right? So like we said earlier, we want to keep track. I'm just going to move this up here so we don't forget to implement these things. We want to keep track of lowest call and largest call, right? So to keep track of that, we'll let lowest call, right? Lowest call is going to start at 0, right? Because root node starts at 0, right? And the largest call is also going to start at 0 as well, right? And additionally, here we're going to say lowest call is going to be equal to the math.min of lowest call, or, right, I actually messed up when I pulled the node off of the queue here, right? We're going to want to destructure this, right? So we get the current node, right, and the column, right? Because remember we said the queue is going to be an array of tuples, right? Then we can duplicate this for largest call, right? We want to do the max. We want to get the biggest column we can get, right? So from there, right, now we have to do the 2 more steps, right? And if we're doing a level order traversal, we want to visit 9 and 8, right? The only caveat being, right, that if we're going to visit 9, right, the column it's going to have has to be column -1, right? Because we said 3 was going to be column 0, right? So that means 9 is going to be column -1. So if cur.left exists, we're going to push onto the queue, right, the tuple of cur.left and call -1. Do the same thing for the right node. And we'll do call +1, right? Because when we go to 8, we want to add 1. 8's column is column 1. It's column 1, right? So if we think about this on a small graph, just real quick, we'll start with the root node 3. It's going to have a level of 0, right? Our queue isn't empty. We're going to pull off 3 and 0. The lowest is still going to be 0. Largest is still going to be 0. Now, does our left exist? Yes. We're going to push our left node on, right, with a column of -1, right? And our right node on with a column of +1, right? And now I'm realizing, right, the step that we're finally missing, right, like we said, we want to create that map of, right, that map of column index, right, to an array of numbers. Actually, might be simpler if we just do this. Right, and the reason I said tree node here, number here, is because the output they actually want, right, is this array of numbers, not the node, not references to the nodes. Right. So if that's the case, what we're going to do is say, right, when you get the array, right, so now we're going to load node into map. So to do that, right, we need to get the array, right, in the map. Now, if the map already has an array for this column, right, we just want to get the array for this column. Otherwise, we want to create a new array, right? In either case, right, in either case, the outcome, we're going to want to push the current node's value onto the array. We do cur.val, right, and then we're going to say map.set. For this particular column, right, we're going to set it equal to this array. Now our output should be that map that we mentioned earlier. All right, if we just check really quick, we pull 3 off, we have a column of 3 and 0, right? Then for the 0th column in the map, we're going to set it equal to an empty array with 3. We're going to push, right, 9 and 20 onto the queue with columns -1 and +1, right? That means we're going to process 9 next, pull off 9, right? We're going to add, right, to this column, -1, 9. It has no children, so we go to 20. We're going to add 20 to the map. It's going to be in column 1. I'm going to put, right, it's going to be in column 1. And for its children, its left child is going to get a column of 1 minus 1, which is 0. 1 plus 1 for 7, which would be 2. So we should be good here. And we'll have our lowest and largest columns, right? So now all we need to do, right, is iterate over largest and smallest columns. So we could say let I equal to lowest call, right? And while I is less than or equal to largest call, we want to be inclusive of our last column, I plus plus, right? And then we're going to have output, which is going to be an array. We'll return output, and then we can just push on the array of values, right, at that particular column's index. So I think this makes sense, except it looks like we have some syntax errors. Maybe it's supposed to be like this. And then we have in car 39, we have variable declaration expected 39. Looks like we're just, okay, this is too big. I can't see the whole thing, right? Thinking variable declaration expected. That seems strange. It looks like the whole thing. Okay, it looks like some. Yeah, it's like just having this. We've flopped the order, so it looks like that created some difficulties. Just parsing everything basically. Push cur.val. Right, and so that was our grave mistake. We didn't make sure to handle, right, that cur was going, that the tree could be empty, right? And they did mention that in our problem statement, but we jumped into explaining how to handle this, right? If the tree is empty, right? If not root, right, we want to return an empty array. And so I think the time complexity of this, right? So we know that for a breadth first search, going to visit every node in the graph, right? That's going to be linear time, but also worst case scenario in the queue, it's going to be linear space as well. And then at the end here, right, we're going to do an iteration of lowest column to largest column, which is really a function of worst case, the number of nodes in the tree is equal to the number of columns, right? For example, we just imagine a root node 3, right, and an infinite number of left nodes, right? Imagine this graph extends out here, could be n, right? So looking at linear time and linear space, yeah, that problem is always a fun problem. So now we're going to be doing number of provinces, right? And it looks like right now we have, right, our goal time is n squared, or our current record is n squared, and our space is linear space. So there are n cities. Some of them are connected while some are not. If city A is connected directly with city B, and city B is connected directly with city C, and city A is connected indirectly with city C. So I think what they're talking about here is like sort of connectivity in graphs, basically, right? I think they're saying like if A is connected to B, B is connected to C, therefore A is connected to C. A province is a group of directly or indirectly connected cities and no other cities outside the group. You're given an n by n matrix is connected, or is connected to I sub j is equal to 1 if the ith city and jth city are directly connected, and is connected I sub j is equal to 0 otherwise. Turn the total number of provinces. So let's map this to our example. Right, there are n cities, right? And I guess n means the number of elements in the matrix, so there are 3 rows, right, n by n, so there's 3 cities, right? And it looks like they're saying is connected, right, n by n matrix. This just looks like an adjacency matrix, right? So we're representing a graph. Right, so if we're representing a graph, right, adjacency matrices are typically used for, I think sparse graphs, right? There's not a lot of edges. I guess so presumably we can assume that maybe there won't be a lot of edges. But if the graph will be sparse, they want us to return the total number of provinces, right? And so I think the cheat code to this problem is the definition of province, right? Province is a group of directly or indirectly connected cities. Basically saying that a province is a connected component, right? So a province is a group of connected components, right, and no other cities outside of the group. How many connected components are there? So here we have 2 connected components. Output is 2. Here we have 3 connected components, right? Which basically means they're connected to themselves, right? And if we look at the adjacency matrix, we can see that that's true. The output is 3. I think the phrasing of connected components, right, is actually confusing, right? Because what it actually, connected component just means that a set of vertices, for example, we take a group of vertices, right? We have a connected component if there's a path to every vertice within the group, right? So since this is an undirected graph, right, we actually don't know if it's undirected or directed. I think the reality is that if there exists a path, or not even a path, if they're all part of the same set, right, then if they're ultimately part of the same set, right, then they would count as one province. So basically we're curious about the number of connected components, right? There's 2 here, right, and there's 3 here. So I think one data structure that helps a lot with connected components is union find, right, disjoint set. But I think there's actually another method of going about this with a BFS from the ADM, right, that lets us work with a parent array, right? And it'd be interesting to see if we can implement this version, because I think in the end this version would still actually be, Actually, this version could be linear time, because with the BFS, we can visit the entire graph in linear time if we build our parent array. No, but in the end, we have to iterate over this n by n matrix. So I think n by n is n times n is still n squared. So output is still n squared. Space is still n. But I think we'll still try this version anyway. So I think this version in the ADM has a lot to do with how you iterate, or some properties about breadth first search, right? Since we're iterating from a particular node to another node, right? We're iterating from a particular node to another node, right? Wish we had a better graph here to work with, right? But I think because of some of the properties of BFS, right, since the newest nodes are processed last, right, if we build this parent array, right, then the output of this parent array actually gives us a path to every single node, the shortest path to every single node starting from root, right? But what we actually given here is a group of edges. This one would actually not be as good because we actually have an adjacency matrix, which I think is still fine. How could you BFS an adjacency matrix? I guess you could just iterate through your BFS an adjacency matrix, right? You'd start at this node, right, which would be node 0, right? And then you would just add the nodes to visit, right, for all that equal 1. That means we'd visit the next node, right, which would be node 2, right? So let's say our nodes are 1, 2, and 3. Starting at 1, we know that 1 is connected to 2, right? Right, because of this 1 in the adjacency matrix, so we know that that's a neighbor, right? So then we visit 2, right? Then we go to its row, right? And we'd add, skip itself, but we'd add 1. Oh, we know that an edge exists between 1, and we've seen it already, so we want to ignore it. And we'll add 1. I think we could BFS the adjacency matrix. So we BFS the adjacency matrix. From there, we want to build a parent array. Right, if that's the case, right, the parent array would just be an array that looks like this, right? And it would have 3 values to start, right? Be -1, -1, -1, right? With the values below it being the node, right? 1, 2, and 3 are the nodes, and their parents are all themselves to start. Right? As we visit the breadth first search, right, I will say that 2's parent is actually going to be, right, node 0. Right, and 3 actually has, we actually never visit 3, right? So in the end, in the array, what we'd like to do, right, is load, right, load load topmost parent into a set. All right, if we load the topmost parent into a set, which means basically I have to do a kind of a recursive function, right? 0, it looks a lot like union find, right? 0 is not -1, right? Which means you have to go to the node at 0. All right, now we're at node 1, right? Does the value at node 1 equal -1? It does. That means that node's set, right, or parent is connected to index 0. If that's the case, then these two are part of the same set, right? So we want to count the number of elements in the set, right? In the end, there'd be 2 elements in the set. Actually, no, we wouldn't want to count the elements in the set. Or basically, we want to count the number of elements in the set plus the number of elements that equal -1. So what we could do is actually this instead. We'll start with 3 as our number of connected components because that's our theoretical max for a given graph. There's 3 vertices. They can all be connected to themselves, which means that for n vertices, the max number of provinces would be n. If we find that a node is sharing, right, the same parent as another node, we'll just subtract 1. The problem being that the worst case scenario to find out the topmost node, the root node, right, for a particular indice could be linear time, right? If we have n nodes, right, if we were to expand this parent array, right, you could have to visit, 500 nodes before you get to, knowing that the first node in the list, you're part of the same set. So if that's the case, this algorithm would actually be much worse than that. Would actually be just this part of finding the number of provinces would be n squared. But that's in the worst case. In the reality, it'd be more like 4n plus n squared. So you know what, to start, let's just try it anyway, right? It's not going to be very fast, but I think there's something to trying to Bfs an adjacency matrix that might be useful in the future, right? So we wanted a Bfs an adjacency matrix, right, to build this parent array, right? This parent array is connected B0. It cannot be, it looks like, right? So to set up the values in the parent array, right, we'll do, right, let I is equal to 0, I is less than is connected length I plus plus, and we'll just do parent dot push -1, right? We'll also have provinces, which is going to be equal to is connected dot length. We'll actually push down here for later on, right? So now we need to Bfs the adjacency matrix, right? To do that, we can use a Q, and if we're using the Q, so we have this Bfs, and Bfs is typically done with a Q, so we can augment it for a matrix. So we could do is, I think we're at least going to need I guess with the Q, right, what node do we want to start with? I actually don't think it matters. I think as long as you start with 1, for example, let's just say we started with 3, right? And we know that our number of provinces max can be 3. We visit this node, right, and our parent set what root node should we start from? If we were to start from a root node of 3, start from a root node of 3 and we have a maximum number of provinces is connected.length, which would be equal to 3, right? If we start, let's say, at a random node 3, then we know that the number of nodes visited would be just 3 and has no neighbors but itself. This is actually even worse, an even worse time complexity than I thought. I think it's, to some degree, you need to choose a root node that at least has one other edge. So I think there's a method that we can use to do this, to BFS through the adjacency matrix. I think we need a method that allows us to visit pretty much every edge, right, in this adjacency matrix, right? But we want to skip nodes, right, that we've seen before, right? So I think that's like a two-pronged approach where we'll have a set, right, which is just going to be a set that has numbers in it, and then what we're going to do is we're going to start at a vertex, right, which is going to be equal to, you can just call it v equals 0. We'll start vertex, we'll say, well, v is less than is connected dot length. Then we're going to want to do some work, right, and to do that work, right, we're going to want to make sure that we eventually visit every every edge in this adjacency matrix, right? And to do that, all you have to do is make sure that if set, right, doesn't have v, right, then we're going to want to do some work, right? Otherwise, we're going to say v plus equal 1, and then here's where we can actually do our BFS, right? So we're going to want right, so if we're in here, we're going to be, right, 0, right, is less than 3, right, and we don't have v in the set, so we're going to do our level order traversal. Though we're going to do that, right, we want to visit all the neighbors. So to do that, we pretty much want to iterate over this row, right, and for every one that is not equal to v, we want to push it on to q to process, right? Our queue is actually going to be empty, right? And we'll say in here, right, while q dot length right, but to start it's actually going to be empty, so we're going to want to do, right, we'll say const neighbor v, right, of is connected sub v, right, to visit all the neighbors. We'll say if neighbor v does not equal v, right, then we're going to want to push it on, we're going to want to push neighbor v onto the queue, right? And now that it's not empty, right, now we can actually do the work, right? We're also going to want to make sure that we do set.addv so we don't revisit it, right? So now we're going to be, right, in this while loop, right, this classic BFS, and we're going to want to say that for a particular vertice, right, we're going to pull it off the front, we're actually going to end up duplicating logic. So you want to do the same thing we're doing here. So to do that, we change this to vertice. We change this to vertice, right? We want to ignore, right, if neighbor.v does not equal the actual the v that vertice that we're on. More aptly called it cur. We're going to push right? So if we look at it right now, the q.length is not equal to 0, so maybe we need to add the 0th vertex to start. Let's say v is less than is connected dot length, which means we have processed at least every vertex, right? Now I have to set v I think we want to switch this so you can do like this: if set doesn't have v, or q.length does not equal 0, then we'd like to do some v is less than is connected. Okay, so I think we can solve this. If we change this from a while loop to a for loop, basically guarantee that we visit all nodes. Say while v is less than is connected dot length, do v plus plus, right? And if the set hasn't seen v before, then we want to do a BFS on it. So we'll add v, and then we'll say right, the current queue, right, is going to be equal to v, while v.length is not equal to 0, right, then we're going to take this vertice off of the queue. We're going to add it so we never visit it again. Right, and then we're going to push all of the neighbors of this vertice onto the queue. But additionally, we're going to say that parent of neighbor v is actually going to be v. And let's just say that we're going to return 0 as a number, right? But our parent array should make sense here. I think we're going to run forever, basically. So we're not skipping vertices that we've seen before. Now I'm realizing we can actually just remove this outer one here. We'll just basically almost start a BFS every single time. Then we should be stopped. Right. So we'll say if set.has vertice, right, then we'll just continue, right, and then we'll add right, otherwise then we'll add the vertice, then we'll visit its neighbors. Right, and so I think, right, we're saying that, right, for these three vertices, right, -1, right, it has no parent, right, but the parent of 1 how do we have a vertice? Right, so we have a problem with v, which is the current. So we're definitely going to want to use vertice, right, and then neighbor v does not equal we want to skip the vertice that started the BFS. Set equal to vertice. say the parent of index 1 is 2. I see. I think we don't want to overwrite it if we write and set. We only want to update the edge the first time we process it. So end set has not seen. We haven't seen this neighbor v before. There we go. So it's going to be set to itself, and the parent of it would be set to 0. Right now we can do the final bit. Right, and so we're going to have a set, right, which is going to be call it root set. It's going to be a new set. All right, it's going to be a set of numbers, right? And basically what's going to happen is actually we can just iterate for const, right? For let I is equal to 0, I is less than is connected dot length. All you have to do is say if parent sub I is not equal -1, then we can just do provinces minus equal 1 and return provinces. V so we start with 0 here in the matrix, adjacency matrix with 0. The only thing we should push on, right, we'll start with 0, right, we'll pull 0 off of the queue. We've not seen this before, so we're going to add it. Visit all our neighbors. Neighbor via so vertice. Neighbor does not equal we didn't make sure that we're only counting edges that exist. Oh, not neighbors. Is connected sub. Oh, a neighbor v of is connected. Yeah. Neighbor v equals 1. The only thing we should push on is nothing. Then we go to x1. onto the queue. Queue length is not 0. Vertex equal to queue 1. We haven't seen 1 before, so we add it. Then we visit all the neighbors of this row. Equals 1 neighbor. Then we set it. We add the vertex. Vertex, we're adding this one to be this one. The vertex there is 0. Vertex there is 0 and the neighbor is 1. It's impossible. So if we follow this through, start the queue with 0. Queue is not empty. Pull 1 off, 0 off the queue. 0 doesn't exist in the set. We add 0 to the set. Right. Then we visit all the neighbors of is connected. So 0 is going to be 1, 0, 0. If neighbor v equals 1, it does. Neighbor v does not equal vertex. Right. 0 does not equal 0. And set it's not, we haven't seen this neighbor. Well, it would fail. So then we're going to do, okay, so next value, which is going to be 0, neighbor v equal 1, no. So we visit the first one. 1 is equal to 1, right? 1 does not equal 0, and we haven't seen 1 in the set. We skip it. Well, 1 is equal to 1. 1 does not equal 0, and we haven't seen it before. I think what I'm seeing, so we have to make sure an edge actually exists between them, is connected. So I think the problem is that we're checking with the specific value at the index. We need to be checking with the actual indice in the adjacency matrix. So for neighbor V, this is going to be equal to connected sub vertice sub NIDX, right? And then here, we just make sure that NIDX does not equal vertice.